I will wait for around a couple more minutes and
Sure.
yeah. Are you back in Los Angeles?
Yeah, I am.
The weather is nice.
Yeah, can't complain.
Yeah. I think we can get started. So,
Okay.
yeah. So, hello everyone. Thank you for joining us today. So, I'm Jian Bian. I'm the representative of Young Members Committee of EEFIT Earthquake Engineering and Field Investigation Team. So, as a brief introduction of EEFIT, we dispatch field investigation teams when there are major earthquake events, and the recent projects include the Turkey earthquake in 2023 and the Morocco earthquake. So if you're interested in this line of work, please keep an eye on our activities and our LinkedIn website, and also please consider joining our team. So this seminar series is organized by the Young Members Committee of EFIT, and we focus on the field works related to disaster risk management. And today our speaker is Dr. Miyamoto, who is the CEO of Miyamoto International, a global engineering and humanitarian organization. And so Dr. Miyamoto is a world experience expert in disaster and post-conflict resiliency, response and reconstruction. So he provides expert engineering and policy consultation to many international organizations, including World Bank, regarding disaster risk management. So today we're gonna hear about the first-hand experiences and the insights that are related to the reconstruction after major disaster events. And now I'll pass the floor to Dr. Miyamoto.
Well, great. Thank you so much. And a good evening, everyone, and a good morning here in California. So let me see. Let me share the screen. Share the screen. How's that?
Yeah, it looks okay.
Good. Okay. So next 30 to 40 minutes, I'm going to present about our experience in the response and reconstruction, specifically in the Turkey and Afghanistan. And this work for last few years. And I'm going to have a question and answer after that. So let's go over this. Just a little bit about our company. We're a global engineering company located in about 30 different locations, 15 different countries. And mainly, as you can see, we're located along the so-called line of fire, fragile area from not only earthquake point of view, but hurricane, flood, and also the conflict. Past 100 years, we visited and worked on the past 30 years, about 100 disasters. I'm not counting, I think 110 or something like that. So we are active in pretty much every single disasters it happens in the world. Turkey, 2023, February, this is what happened here. It's magnitude 7.8 and 7.5 back to back. And this is the southern part of Turkey, bordering Syria. It affected over 300 to 400 kilometer long and also 100 to 200 kilometers wide over that area. So this is a huge earthquake, and any means 7.8 and 7.5 back something I have not seen that for a long time, especially in a densely populated area. It's affected about 40 million people. Terrain is beautiful, just no question. But also same time, this geographical beauty makes it very difficult to respond and recovery the pieces like especially a lot of remote area. Impact affect about 14 million people in a strong motion area. And it caused the 50,000 fatalities over and 100,000 injuries. About 4 million people are displaced. And financially, about $100 billion of direct damage. This is essentially the built environment. On top of that, usually 3 to 4 times bigger actual indirect damage, such as loss of jobs and many other elements of it. So I might say this is probably one of the worst earthquake disasters I haven't seen since probably Sichuan, China. And this picture I took from Hatay, it's complete destruction. Amazing. So we did the assessment, both a combination of a satellite image and also the on the ground assessment. Based on this, we counted about 1.7 million buildings in this affected area, and it's typical buildings. Buildings are usually the just residential, 3, 4, 5, 6, 7, 8, 9-story residential buildings made of concrete. And you can see here, 35,000 buildings collapsed, about 2% of stock is in the first shock. And about 11% of buildings, which is 200,000 buildings, severely damaged, or many are not salvageable. So you're looking at about 230 to 200, about 250,000 mid-rise buildings that probably need to be replaced. But however, about additional 500,000 buildings, that's what we call yellow tagged. That's a light and moderate type of construction. But if you see the bright side of this thing, about 60% of buildings are actually unaffected or very small minor architectural cracks, pretty easy to repair. But right after the earthquake, what happened is the population who's affected living in a yellow, even a green type buildings, they feel very uncomfortable to go back there. So there is the major issues in the internal displacement people issues which Turkish government faced. So why this happened? Is this because the engine's bad? Because of the building codes not good? Well, there are a few reasons. The Turkish building code, it changed in 1998. This is seismic components of it. So anything built prior to that, around 2000, anything built prior to 2000, there is no earthquake consideration, no ductile details, none of this stuff. So that's really dangerous. Second, there's no license system for neither contractors and or engineers, and no inspections required by the engineers for the privately owned buildings. So as you said, this is the typical building you see out there. small, apartments. Some are pretty sizable though, 100 units and 150 units and stuff like that. But it's a reinforced concrete system, and it filled with the masonry infill. These are some of the typical structural damage you see. This is a lucky one, did not collapse. So this actually, believe it or not, it's met intent of a building code, because of what we engineer buildings, doesn't matter Turkey or US or Japan, the intent is provide a life safety minimum. So building will sustain the major deformation, so major failures, what we call inelastic behaviors, to absorb the seismic energy. So this is actually normal thing what you're looking here. Is this the repairable? Probably not. I mean, first of all, it's quite a bit of a tilt happened based on this, and displacement, permanent displacement, and also most of the people don't want to go back to the house even it's being repaired, because it doesn't look so good. But many cases that we do get into repair of this kind of things, but when we do that, we add additional lateral force resistant capacity, like adding the concrete shell walls or wrapping all the columns and so on. The main failures come from the not following the construction protocol. As I said, there's no engineers on the field for inspection during the construction. So I saw a lot of defect like this, like using a smooth rebar, or does not have enough confinement, details isn't quite right, and aggregate is like smooth, big rocks. Essentially, you see things like that in the mixture. And obviously, older stock of buildings, like a self-storage one, become like that, as you can see. But there are many failures, which you talked about, about 30 to 40% buildings are severely impacted, but 60% buildings they're not, and many actually belong to the public sector buildings like hospitals and schools, viaducts, roads. I mean, those are actually the fairly untouched. So here's the video of the hospital. This is a base isolated. So that's the isolation phase. So you can see that actually the building is sliding back and forth to absorb the energy. So, there are about half dozen hospitals in the most severely affected area, and they are designed using a base isolation. And base isolation is essentially what it is a building, sits on the ground. So when the ground shakes, we move with it, and it causes the inertial force and deformations, and that causes the issues, right? But if you provide the air gap per se, ground can move much as it wants. Obviously, we cannot provide the air gap, so provide the this rubber or friction pendulum isolation devices, which is essentially roller. So it's just that decouple from the ground motion, essentially. That's the base isolation is. So there are 12 hospitals like that. They're not only did not get damaged, but they're fully functional after this major earthquakes. That's pretty incredible. So this is not something about the technology is lacking. There is a great knowledge in Turkish engineering community, and building codes is as good as anywhere, and education is good as anywhere. But the lacking of inspection for the private sector buildings, that's the cause of this incredible destruction. This is Hatay we talked about a little bit. This case is the about 40% of building stocks damaged, and especially the downtown core, as I would say, essentially 90% buildings, they are damaged heavily. Something like that you see. The reason is this is the big river coming through, and a lot of soft soil going on in the area that causes the amplified motion. But this is the same building, similar building in right next to the disaster area. This is a well-built construction. You don't see even a scratch, And damage itself is a very random. This is a town of Gaziantep. This is the one of the large major cities there, and 97% there is no damage at all whatsoever. Why is that? Well, it helps, rocks. So a city itself is sit on a very hard soil or hard rock, and so that ground motion did not amplify much, even it's right at the epicenter. So what we did is we tried to assist the Turkish people and the government by the hitting the gaps. The Turkish government is really tied up to addressing the total collapsed buildings and also the severely damaged construction itself. But there's, as you saw, there's a 30 or 40% buildings which are moderate to light damage, and also the green buildings which may have certain cracks, but people feel uncomfortable going in. So we got funded by USAID and CRS and the Habitat for Humanity to how to provide the solutions to this light, moderate, and undamaged construction. People can get repaired and get back to home. So we actually assessed the almost 24,000 undamaged buildings and 12,000 of light damage on top of that. This assessment is not only just damage assessment, but actual repair quantify assessment. So engines go in there as an app, just measuring the cracks, be able to come up to BOQ right on the spot. So the residents can really act on it quickly. And we reached about 150,000 people in person and over 2 million people in different media outlet, including public mass media like this one. Now, so the one thing I want to talk about the emergency response components of it. As far as the response is concerned, the way the Turkish government did is something the best practice I have ever seen, actually. And I was on the site 48 hours, after the events, and that time there is the something like a 50,000 to 100,000 emergency response people on the ground, and every city or villages I went, there's organized the tent cities built up, the warm tent, and roads is completely cleared in a day 2, and I can reach to anywhere by the car, and internet is fully available. And airport, Hatay Airport was damaged, but it's open, and after 4 days after the major event. And it was an incredible, robust event response. I saw that, and there's emergency response, the urban search and rescue team. I found them at every single places there. It's a lot to do with the Turkish, government. They are preparing for the Istanbul earthquake, kind of 20 million people. So it's just they have this incredible capacity and awareness of what to do. So that's what really helped them. I think they saved thousands of lives out there, just having that preparedness itself. But challenge now is that how to reconstruct this 250,000, 250,000 heavily damaged buildings and additional 500,000 moderate damaged buildings. And, it's a big deal. Talking about the new construction, even the economy is small scale, it will cost $1 million to $2 million to reconstruct the typical apartments like that. So, times 250,000, as you can imagine, it's a huge amount of money. So right now, Container City is built in many different places. You can see in the right bottom corner, and government's built in the this new construction outskirt of that. This really tried to address this heavily damaged construction piece, but I think that one of the things we had to look into the moderate, medium damage construction, which you can see on the left side. Some certain structural damage exists, but it's definitely repairable and it's strengthenable. I think that's very important to do that. And otherwise, that you're going to end up to see the so-called donut effect. There's nothing in the middle of a city, but everything built up outside. You don't want to do that. You just really lose the whole community concept. So repair component is very important. Not only cost effective, usually it's used in the repair and strengthening. You're looking around at average about 20% of a replacement cost. So essentially 1 for 5, deal you can make that. So now let's fly back to Afghanistan. There's a total 2022, there was an earthquake, which affected almost 100,000 people and destroyed the houses. And this is a very fragile area. That's where the southeast corner, that's where the Taliban would actually originate from, and it's the border of the Pakistan border. So first, we done again the remote satellite based assessment to understand the damage index. So when we do it, we overlay the before and after picture, before the earthquake and after the earthquake picture, and we overlay it, and understand what is the displacement look like, and based on displacement, we tag them. And we've been working with the NASA JPL for almost 10 years now for refine the system, and I think now it's definitely deployable. Something we use that maps quite a bit, especially the Turkish earthquake, to guide our team to go places. So based on this, assessment is collapses 17%, almost 20%, and yellow tags is the moderate damage one, but still repairable, 50%, and greens are 30%. So as you can see, 70% of the building, some certain impact was there in the area. Here's typical construction look like. It's multi-family residences made of clay, or partial wall system. So here's a social structure made up like that. Usually we notice about 30 to 40 people live in a compound, and it has a large walls, and all the social activity happens inside the courtyard. You see agricultural land inside, and a playground, water, the animals. Just that's how the urban structure built like that. It's actually a very important part of this thing is a privacy to the women. It's very important. Their appearance and noises cannot be public. So in a compound system like that, that women are free inside. But it's a very important concept. I know it doesn't quite, for the Westerners, quite, we don't maybe see the reason of it, but that's a cultural system like that for thousands of years. And I'm not here to make a judgment about good or bad. We just, as a humanitarian, that our job is to repair, construct back to the houses and villages so people will get back to normal condition as before. So this is a typical system look like that. And I must say that we found a lot of genius in that structural system. This is the roof purling, kind of just embedded into the clay wall. And what happened is that almost like this friction devices. So what was actually going back and forth in the rocks, and that roof purling or beams embedded into it. So there's enough bearing lengths, which in many cases also enough bearing lengths. The wall moves, and I saw a lot of damage in the wall, but that's actually causing energy dissipation by the friction action. But the problem is that if there's no enough embedment into the wall, it falls off. So that's why most of the people actually died. It's like this. And also the clay roof itself, many houses they don't replace yearly basis. They keep adding it, so it becomes thicker and thicker and thicker. And obviously, that the heavier the mass would be, the bigger the earthquake force would be. So how the vernacular construction worked here? How does earth construction work? Just made of earth, no cement, nothing, no aggregate, just that. Essentially, if you compare the cement concrete and a clay concrete, very similar aspect of it. Cement has a gravel and sand, provide strength, and cement to just combine together. Clay construction, same for this particular case. Sill, sand, everything else is essentially combined by the clay itself, just like that. So we actually brought the clay construction expert from France, actually, and they sampled the manual sites to do the cohesion test and many other tests to understand the what makes works and what makes didn't work. I mean, findings essentially the traditional housing is unique, and if it's built right, is a very, very robust earthquake resistant system. Use the concept of rocking and friction movement of the elements, and it's everything locally available. You can harvest this clay and rocks from on the ground right there, and to build this construction. This is actually very important, especially a remote area like the Afghanistan over this Pakistan border I was talking about. There's no way to bring some steel and concrete. I'm sure there are, But problem is it's not sustainable. It's not like they can do that forever. So it's more important things here is to understand what is the strength and the weakness of this molecular architecture is like, and specifically address the weaknesses, avoid that, and emphasize the strength. And that's the whole capacity building components of it. And our engineers trained something like over 2,000 local masons in the area, and we provide funding to actually repair those houses using that labor. So we create a very simple key technical message, such as the height and the thickness ratio of a wall. They're usually 50 centimeter wide, 5 meters high, so that type of thing. And also the bean clay, really important thing is the protection. They have a plastering system, and that has to be there. It's very important. Otherwise, clay does melt. And down the bottom, the foundation's well-built construction made of rocks. That's actually very important to prevent corrosion, provide the protection from a flood and the water. And the roof thickness itself, yeah, they have to replace that. We just make sure that not more than 8 inches. That's something that we insist on that. And most importantly, the bearing length to the purl into the wall. So these things, it's not like we invented it, by the way. This is something that we extract this knowledge from the master masons in the area and how they see that the best way to build. And we use the knowledge, we analyze it using the finite element modeling to understand the safety factors and what kind of earthquake can take. And we convert that key technical message like this, a very simple message, and build the capacity in the villages and the masons and the contractors in the area to facilitate their own reconstruction. So now this particular message is not only useful right now to reconstruction back, but also it will impact the generations of masons to come. I think that's a very, very important concept. This is something we used everywhere. In the Haiti 2010 earthquake, which killed about 300,000 people, our team over the 2010 to 2015, we trained over 10,000 masons. And to this day, you see the impact of how people built, in the remote parts of Haiti. Just that knowledge is probably the best thing we can share with. So it's one of a broader campaign. Training is not done for the adults masons, but this is students, the kids, just have to widely disseminate the message as much as possible. It's it's a beautiful country, no question about it. This is one that they reconstruct. Now they're fully occupied, and personally, the way they built is that essentially the evolution of this vernacular architecture took them millenniums to get there, right? Just knowledge of this wisdom and the thickness wall. It's inside is actually very warm in the warm in the winter and cool in the summer because of the thickness of clay and the roof clay. And it's actually very nice condition up there. It's that's something it doesn't mean that our way to do in the Western way, using steel and concrete and plastic, in the glasses, that's a better. No, it's not better in many parts of the world. Have to get in. So, we're working with the de facto authority, this Thailand government. It's very important, and I know they do have a really serious international issues, but I know they want to change that, and hopefully they will change the certain policy elements, and especially the gender equality piece of it. I think that will make a huge impact in how the international community sees the Afghanistan. They want to collaborate, just no question about it, and the people need us. They want to work with us. I'm talking to villages. I'm talking to people living in the town. I'm talking about professionals, and I think that this type of activities, I'm hoping for to open up the some different relationship than what we have right now. That's about it. Thank you.
Thank you for the very interesting presentation. If anyone has any questions, please feel free to raise your hand or just unmute yourself and you can just jump in.
Yeah, anything would be good. I can talk about response components to structural systems.
I think we have a hands up from Andrew. Andrew, do you want to, or?
I think you're on mute.
Yeah, right. I allowed the mic.
Hi.
Can you?
Hi, kids.
Hi.
Can you hear me?
Yes.
Fantastic. I absolutely loved the presentation. That was amazing. I wondered if you witnessed any occasions where a building has actually slipped from the roller. Did they actually maintain fixity in all the cases that you looked at?
Are you talking about the Afghanistan or Turkey?
Turkey, sorry. Apologies. In Turkey.
Turkey. You mean slipped? You mean
Yes.
Like a slight slid off, you mean?
Yes, that's right. I just wondered if you'd seen any instances where actually the system, the building has maintained its location, but effectively it's come away from the rollers. Whether you observed that or not, or did they remain robust and stayed within that location?
I want to make sure I understand the question. So essentially, you're talking about geotechnical failures, or
failure at the foundation, where the foundation interfaces with the building. Yeah, you've got the roller system, haven't you? I just wondered if it had actually taken buildings off the rollers.
Oh, base isolation. No, essentially, the way the base isolation works is so building sits on base isolators, and base isolators it has a moat around it. So essentially, that designed for maximum distance, so it doesn't hit. So once if you under design it will get a hit, then we'll have issues with it. But if it has enough surroundings, gaps in it, so therefore buildings essentially three-dimensionally or two-dimensionally just can't move around anyways, so it does not slid off like that. It performed really well. Wow, I don't think there's occasion where the base isolation failed in the past. In Japan, I noticed one hospital did fail it was a near earthquake. The reason is the moat built around it. Over the years, people used the planners and stuff like that, so they didn't know what exists. So then at the base isolation did not activate it, obviously, so it did not work out that particular case.
Wonderful, thank you very much.
Yeah, and geotechnical failures, though, I do obviously notice a lot about liquefaction type of things going on in the Hatay area, and you see many more buildings tilted over and so on. But generally speaking, the geotechnical failures in liquefaction, generally speaking, doesn't kill people. It's just tilt off and people, escape from buildings and so on, which we see quite often in Japan. Whereas the liquefaction is a big deal. And I think the only occasion I saw liquefaction really killed a lot of people is the Indonesia Palu earthquake. That particular case, liquefaction is essentially almost like a horizontal tsunami event. It's just unbelievable. A horizontal landslide, almost. So it actually swallowed many villages there. But that's a really rare occasion like that. Usually, liquefaction is an issue for the be able to occupy or performance, but it does not usually threaten the lives there.
Right. We have several questions in both Q&A and chat, so I will just read through in the order that were posted. I'm not sure what this exactly means, but Newman asked if how we should connect the beam to the wall. Any detail? That's the question.
So this is at Afghanistan, right?
Yeah, I will try to give. I will give the mic to Newman, just in case if you want to jump in. Yeah, I think so, right? Yeah. Mm-hmm.
Yeah. Hi, I'm Numan. Thank you for presentation. My question is that how to connect the beams to the walls, and also the base connection of the walls that the system that you propose for the earthquake resistance system of Afghanistan.
Yeah.
Could you any further detail?
Yeah, sure. Actually, you don't want to make any connections there. So partial walls are 50 centimeters thick, and many cases actually that there's a hole through this. So the purling is that go through the whole wall, has no connection. Some cases I saw some smooth rocks down the bottom for bearing, but essentially concept here is a walls to rocks, rocking back and forth. So if there is a connection, it does not, you're just going to go with it. It's actually much more dangerous. You will not disconnect that. So I know as a structural engineer, usually we want to provide some robust connections and strength and so on like that. But sometimes make it stronger doesn't mean it's actually better. And this particular case is you want to keep that walls to freely moving and have the energy dissipation in it. More the movement in the structure actually does cause the more energy dissipation. And especially having a clay construction like that, I think is very important. But way the rocking works out, not actually single motion like I was showing animation. Actually, it's there's the gap. There's the construction is the chunks of about 15 centimeter high. There's chunks of a block built in it. So use the horizontal cracks in the throughout the essentially joint. So it's moving like a whole bunch of blocks moving back and forth. Actually, it's a very similar phenomenon as the towers. In many cases, the ancient these towers made of rocks survived through the earthquakes pretty well. That rocking motion of this independent of a rock, rocking of it. So connections are essentially the nothing. The clay wall built on top of this rock base wall per se, made of rocks, and they're the reason for the water penetration prevention. But just the gaps happens or there's a rocking happen from where the rock interface the clay wall itself.
Okay, thank you so much.
Sure.
Yeah. I think Jacob also has a question, and I also had a very similar question. Jacob, I gave you a mic. Do you want to ask yourself, or shall I read? Okay, I can do that. So, for the partial construction, the traditional technique is that is passed down through practice and the word of mouth. And then, so have these and other traditional techniques been researched with an aim to standardize the construction?
Yeah, yeah. Actually, if you go the Afghanistan, and this particular wall construction is pretty unique to this particular area. If you go north, actually, the people build differently. There's a dome constructions, and there's a certain study what's done for understand the traditional technique or vernacular architecture technique. We observe, and this particular things we did is the extract knowledge from the master mason because we notice that many people are built differently. They are cutting essentially corners, And I told one master mason talking about, he goes, man, those people are crazy. They did a really dangerous thing. They should not do this. They should do this. So there's knowledge does exist. It's just the some people just don't want to follow it. That's why it causes death. So our whole main mission here is to extract that traditional way to do things and back up with the science and disseminate the information as much as possible. So that's it, our aim is there. And we are actually in a discussion with some UN agencies to actually create the kind of categorize the different type of vernacular architecture in Afghanistan to understand what's the strength of those construction and try to disseminate the information. That's something we're in discussion phase right now.
Thank you. And there was another question from Catherine that she said they read that the government had relaxed inspection requirements for construction in Turkey in recent years. Do you know any information in this line that if the government had relaxed inspection requirements in recent years?
What kind of requirement you said? Inspection requirement? Inspection requirement? No, it's inspection is required for the public infrastructure, viaduct or large construction. and they performed really well, exceptionally. As I said, none of them viaduct is, some damage is there, but they're useful after this magnitude 7.75. It's pretty amazing, actually. And airports, it's open, right, after 4 days. And but the inspection was not part of a norm or building regulations for privately owned buildings. That's a huge issue. I think it's pretty much exists in many countries, by the way. So there's a great body of knowledge in engineering and a great building codes, but actual implementation in the field of privately owned buildings doesn't exist. That's true in Turkey, that's true in Indonesia, and I see many parts of the world, same issues we have. But that's a huge issue because that's where the multiple deaths come from. Because 90 to 95% of buildings are residential construction, private owned. That's true for anywhere. And so inspection of that is really very, very important. And we have an office in Istanbul for many, many years, and they never want to take the private sector works for, like, especially apartments and stuff like that. And I just wondering why they want to do that. And yeah, he did tell me the fact is the just not able to inspect the building, so they just felt uncomfortable. So I can see now why.
And there were another question that what were the dominant factors and issues delaying the start of repair and reconstruction in Turkey and Afghanistan?
Yeah. Which question is that? It's a number one.
By Blagojevic Nicola. Nicola. So in the chat.
Oh, there you go.
Yeah.
What are dominant factors, issues delaying the start of a repair and reconstruction in Turkey and Afghanistan? Let's talk about Turkey a little bit. So, it's a lot to do with a massive scale. You're talking about 250,000 buildings probably have to deconstruct and rebuild. 250,000 buildings, each of course probably $1 million. So we're talking about $2.5 billion. It's just huge amount of, $250 billion. So that's huge amount of money needed to do things like that, right? And on top of that, there's a 500,000 buildings people don't want to move back because some certain minor damages in there. So just that massive scale, no government cannot do that. Same thing happened in California. There's no way California State or FEMA can act fast on what Turkey is doing there. Just massive scale. That's really the issue. And I think that we have a notion of anything bad happens, government will come, UN will come to rescue or reconstruct. That just doesn't happen. If you look the disasters in the past, approximately somewhere between 5 to maximum about 15 to 20% of the damaged assets is built back by the government. Rest of it, 80%, 90%, has to be done privately. So that's why the really important fact is the open up the investment to the private sector to be able to reconstruct. That's actually a really important part of it. Japan did the really one of the best practices I saw in the Kobe 1995 earthquake. Killed 6,000 people and destroyed the minimum residential buildings, both the earthquakes and the fire. But the town was pretty much essentially reconstructed in a bigger and better, stronger, within about 3 years. Because what the government did to make sure that the private sector investment from Tokyo and other places happened to make a attractive investment. That is actually very, very important. That's something that in the humanitarian sector, we don't talk about that, the role of the private sector, but that's such a key piece of there. Make the investment easier, and the towns and city can get reconstructed much, much faster. Now, Afghanistan, since it doesn't have the investment, anything like that, I'm talking about this high desert. I'm talking about, I don't know, 8,000 feet high area there, right? These little villages. So there's no investment or money, anything like that. So their most important thing is do not bring in something people don't know. I saw the one UN agency, they brought in this large concrete boxes. Essentially, they built this concrete boxes as a housing units out there. Cost about 10,000 per unit. It's horrifying results. Number one, people don't want to live there, especially without no walls, especially women. They don't want to live there. because privacy is very important. Not only appearance, but the voices and noise is very important. So you cannot live there. So that's the number one's wrong. Two, the locals, they don't know how to deal with this concrete construction. So after 1 year, we visited, it's leaking, right? And they don't know how to fix them because concrete is something they don't deal with. So those are truly a bad practice. So try to bring in something new thing, something completely unsustainable, to the local setup like that. But I see that over and again. Just the humanitarian sector, they love to do something that keep doing something doesn't work. I think the most important thing is really to activate local, knowledge and the people and the capacity and keep the money in a local level. That's really the way to go. That's the only way to go.
There's a question from Bactus that what to think are the best common ways to support long-term recovery after those earthquakes and preparedness for future disasters. I think I also had a similar question because recently I was working on a project that how we should prioritize the reconstruction of infrastructures. It should be either transport or education. So, and all these are related to this long-term recovery process. So, and also in addition to that, Bectus is asking about preparedness as well. So I think it is related to the policy.
So let's go back to Haiti. I talked about the 2010 earthquake, right? Massive scale, 300,000 people died and affected something like 250,000 buildings being totally damaged. And we have an operation there since 2010. And 2021, there was a magnitude 7 earthquake in the southern part of Haiti, the Skolakai area. Just massive scale. It's a jungle-ish area, and I spent quite a bit of time down there. And one day I was just walk around the jungle, and I saw this construction site near a small village. And this construction site, new construction, I saw the masons working through. They're building a little school, and what I saw was pretty amazing. They have this. They're making the hoops with the rebar, right? They have this ACA 318 100% complied, just detailings from hooks to spacings to sizes, everything about rebar for these columns. And I was amazed. I go, wow, you guys do such a great job. And I was talking to Mason, how'd you learn this? Did you come to our seminars, 14 years ago in Port-au-Prince? They said, no, it's what are you talking about? It's a pretty normal thing. I learned this from a trade school across the street. So that becomes like a norm of Haiti. Yes, there's a lot of issues today, a lot of political issues and bad things going on. But as far as the capacity of a normal mason's concerned for seismic resistant system, is a hugely successful, just no question. So anywhere I go in Haiti today, pretty rare to see the so-called non-confirmed detailings, especially in concrete, even at the really poor area. So answer your question, I think knowledge, capacity building components, especially in the laborers and the masons, I think is a very, very important. We talk about a lot about building codes all the time, but building code is not, most of the countries do have great building codes, by the way. And it's must have been changed and it's just there. It's not, I don't think that's that where issue is. Issue is not even engineers. Each country, if you go see each country, it doesn't matter if Haiti or Japan, top 10% engineers, they're really good, no matter what countries I go. They're highly educated. Many cases they're got a graduate degree from MIT and, place like that. So it's not about engineering. It's just about how actually the engineering practice is the implement on the ground. That's why the inspections are most important. I know my solution sounds like pretty simple. Say, okay, Turkey, just have an inspection. But that's true. Such a basic things are missing, So yeah, I think the capacity building and the contractors and laborers is probably the best thing for the just the reconstruction, now, and also the preparedness for the future event. But remember that we have a window of gap about 5 years. Big earthquake happens after 5 years, no one remembers, So that 5 years is very important to be able to do a lot of things there, for the prepare for the future.
And there was another question from Matt that what percentage of your employees work in the field versus working with remote data, like satellite data? He asks, as a one-year PhD remote sensing student already considering post-career options. So on the Q&A, on Q&A.
Oh, it's on chat.
No, on Q&A.
Q&A. Okay.
Yep.
Do you mind if you repeat the question again?
Yeah. So, what percentage of your employees work in the field versus working with remote data? Because he's asking, as a one-year PhD student, working on remote sensing.
What's the percentage of it? You said?
The employees that work in the field versus just work in the office using remote data, like satellite imagery. I think he's looking for an option, post-career options, and he was wondering, like, what is the general scene that your companies work, like employee competition?
Yeah, sure. I mean, essentially, for example, I'll give you an example. The Turkey earthquake is a pretty good one. We have a team in Delhi, India, who actually do that remote sensing, analyzing it. They get the satellite data image and they use AI to identify the building footprints and overlay the before and after pictures to analyze that. And we do that not only for earthquakes and hurricanes, but also the conflict. So we done mapping just now for that Lebanon. How much of damage is actually caused, and where's the locations of that, what kind of things has to be done, and on the ground is we don't usually. I mean, depends on the places. Like in a place like Haiti, we may do assessment, but many cases we get into actual repairability, kind of things. So it's combination of damage assessment and the repairability assessment and the BOQ, the billable quantity assessments on the spot. So we program the app to do that. So engineers can just measure the basic information in buildings to get the cost of essentially measure methods and the cost of a repair, that kind of things we do. And local level, most important things we do is engineers do. We hire locally. For example, Ukraine, we have about 70 people today. We have 69 local engineers and one international. I think it's a very important to have this local piece exist because there are a lot of good engineers, in every single country I go. Because after disaster, what's most important things there? Yeah, of course, people need food and water and shelter, but more equally important is the job. Because people lose jobs because society is not functioning anymore. So that's our approach is to create jobs locally. So not only providing technical solutions, but filling the gap of the so-called job loss components. I think is very important. But yeah, I mean, if you're interested to working with us, just send me information and then we can figure it out.
Hey Matt, does this answer your question? I think you can unmute yourself. I gave you a mic if you like. Okay, then I think we can move on to the next question. That from Ethan, what countries have you come across that you have a very good approach these events, and what should be the mandatory measures in place for areas prone to earthquakes?
Which countries?
Just any countries that you think the best at.
Oh, I think Japan. There's just no question about it in my mind. I think a lot to do with the well, I was in this US Japan New Zealand workshop and earthquake engineering and stuff like that, like yesterday actually in San Diego. So 3 engineers from 3 different countries talking about their practice and so on, right? We come to conclusion Japanese is most ahead, and we conclude why, because they have this every 5 years. There's a major earthquake happens, so their practice and engine practice and also the social expectation of the engineering, and what works and what doesn't, and recovery process. They understand because they do this all the time. Other hand, in the U.S., the last major earthquake was Northridge 30 years ago. And that was not even major. That's a magnitude 6.8, 6.9. It's a moderate kind of earthquake in a suburban area. California never really had experienced the true urban disaster since 1906. So I think just looking at US building codes and stuff like that, we tend to overanalyze a lot and kind of get into this really detailed nuance of this probabilistic assessments and so on. We do a lot of that. Japanese, on the other hand, they don't do none of that. They just do it. They use the state-of-art technique, using the base isolations, energy dissipation devices, dampers, you name it. They put pretty much every single major construction, they use technique like that. After there's a 10,000 base isolated buildings in Japan versus in the US, maybe a couple hundred, but it's a lot to do with the public though, because of every 5 years, major disaster happen in Japan, right? There's like public awareness, keen awareness of what works, what doesn't, and they appreciate the good engineering. They appreciate the investment more to make a more resilient construction. You don't see that in the US because there's no public support, right? Because 30 years ago, and people say, "Oh, there's no earthquake here," So it's a lot to do with the frequency of it, So
But
yeah, and
but when we think about the effect of these investments, and if there's no there's a less frequent earthquake risk, then do you think it's better that we just do less investment and deal with it later on? Because the return on this investment is quite low, and seismic retrofitting is clearly a very expensive job. What do you think?
well, I think it's a myth. I think and seismic strengthening is not expensive. I say somewhere between 2% to maybe 20% maximum of the replacement cost. And also the seismic strength to what level, right? You want to think about it a little bit. I think that they sometimes become unaffordable. For example, in California, we have this regulation called the SB 1953, which essentially require the hospitals to seismically upgrade it. We adopted things, it's got to be like 30, 40 years ago. Deadlines keep pushing it because it's not affordable. Doing a seismic strengthening in a hospital which is being occupied, going to provide certain minimum requirements, like say life safety or something like that, right? It's just not affordable. You're right. But approach shouldn't be like that. Approach should be like, what is the affordable amount of money you can spend on that? Spend the money, because let's say that if you do right way to do things per engine standard is, let's say, $100 million doing it to make it right. But problem is that $100 million, no one has that. But if you spend $10 million, it's actually cut back the probability of collapse a lot. There's certain major deficiency exist in many deficiencies there, but there's certain main key components there that addressing that piece like that, it makes a huge impact. For example, what LA and California done right is what we call soft story ordinance. Essentially, we know so many of the apartment buildings, 3, 4, 5-story apartment buildings, collapse at the ground level in a Northridge, earthquake. So ordinance said reinforce the ground floor, so it doesn't have the soft story, this mechanism of failures, right? It was very affordable, couple $100,000, maybe even less. You can strengthen this open parking garage area at the apartment, right? So yeah, it's actually going on really strong, about 10,000 to something like 13,000 apartments like that being repaired today in LA, So has to be like a pinpoint approach, has to be affordable. You're different, right? If you just arbitrarily said, fix this to AC 41, BAC 2 level, nothing will happen. You're right.
Yeah, I agree. Yeah, thank you for the insight. And
Mhm.
uh, uh, And I think another question from Ethan was, what are the mandatory measures that you think very critical that always should be in place?
For the building code wise, actually, this is a discussion we talked about yesterday in a conference. We call drift ratio, which means essentially how much building can move in a major earthquake. Japan, their target is around 1%, which means that if the 100 meters high building, that 1 meter can move. That's a target. In the US, it's 2 meters. Well, most of the world is 2 meters actually. So it's actually the damage is a lot. Not only structural systems are permanently damaged by the energy, by inelastic behavior of energy absorption, but also non-structural elements like non-structural stuff, pipes and everything, furnitures and they bricks. It's 2 to 1% huge deal. So yeah, that's I would. If I was governor of California, I'd tell everybody 1% limit. that will change the profile of the earthquake risk a lot in the state of California.
And you don't think that will significantly increase the construction costs? It's something that can be done?
No. I mean, maybe like 1%. It's just not much. It's just that the structural cost is only 20% average of the total, construction, pretty much average global, right? So even adding the 5% more for structural costs, you're talking a very small fraction of that construction cost increase. In a, when we engineers think used to, we just put stuff in it, like seismic damping devices. We didn't tell the clients about it. We just put it in there because that's the important thing to do in a certain area. So we tell the clients that's what we're gonna do. We don't give them options, And I think engineers have to take a lead like that to be able to tell clients what is the right things to do, But you got to be creative to make sure the construction costs stay the same. Yeah, if you spend at the 10% on construction cost, there's no way they will say, yes, please do. They're going to do that, Has to be very affordable to do that.
I think this could be our last question from Walkers, that they have a question that why countries have different building construction codes, and can an engineer design a building using Euro code in India apart from IS code?
Building code? I don't think building code is really, you don't want to use building codes, You want to use the physics. You know what I mean? I mean, especially like an earthquake environment. I mean, building code is like a moving target. Whatever we think today, probably illegal 5 years from now, right? Seismic hazard, whatever we think today, probably wrong 10 years from now. Wellington, New Zealand, they just changed the earthquake demand hazard by 2. So it's not about building code. It's about that they really understand the physical physics of how the building behavior and under the seismic motion, and you need to provide something it works. Like I think that in Japan you see the actual destruction getting less and less and less, since COVID, by the way, and it's a lot to do with the use of energy dissipation devices and dampers and stuff like that. That's actually it's something that we know this long time. It works, but people don't do that. Engines don't do that. So what we do, engines do, we rely on this vertical loading resisting elements like beams and columns, to absorb this seismic energy, what we call ductility. Right? You with ductility to deal with. That's what we do in the US a lot. That's wrong. That's a really technology of 1960s, Sure, you want to have a ductility as a backup, but I think that the main system should provide a certain different energy dissipation devices to absorb energy before transfer to the backup, So that's how we can create a much more resilient building and a resilient community that way.
That's very useful to know. Yeah. So I think that was our lecture for today, and thank you very much for today's talk. It was really insightful. And so have a nice evening and have a good afternoon in Los Angeles.
Yeah, thank you very much, everyone.
Thank you.
Bye.